How would one make an HTTP server using the new Zeek I/O interfaces? Let's find out. Zeek 0.16 HTTP server example. Let's have a look. Okay, I see. That's interesting. I see. Ooh, okay, that can't be right. Okay, there are some glaring problems with the AI generated code. Now, I did repeat this exercise with another popular search engine, and I ran the search a few times. Now, while there are some variations in the output, this latest result is representative of the problems that I would typically find in those AI summaries. So, since a lot of people might get themselves stuck simply reading the AI summary, I decided it's probably a good idea to get yet another simple HTTP server example on the interwebs. So, in this video, I will use a version of the AI generated code. I will point out the problems and I will improve on that example. I'm going to start by creating a simple Zeek Hello World application. Now I'm going to speed run through this and I will slow the video down once Hello World is printed on the screen. Okay, let's paste a version of the AI generated code and we'll call it from our main function. Now, something that seemed very unusual are these two buffers. So the AI says there should be 1 byte. Now that's unusual because typically one would want buffers to be relatively large. So I suspect this won't work, but let's give that a go. Okay, so as I expected, that is not working. Okay, so let's go back to those buffers. Now these would need to be arrays, and I think 8 kilobytes should be quite generous for a buffer size. Now I'm multiplying by 1024 because I'm old enough. This is what we used to call a kilobyte when I learned things. Then I want to pass these arrays through as slices. Okay, so that should definitely fail if somebody tries to change that back to a single byte. Anyway, so now we should be able to run the code and we'll be able to demonstrate our very first problem. Okay, so it's doing something. What I'll do is I'll start curl in a second terminal and okay, so curl got the response, but then our application crashed. And okay, it failed because of an HTTP connection closing, because curl closed the connection when it finished running. Okay, so let's go back to where we call the receive head function. Now receive head can fail Now this might be part of a typical workflow where the client simply closes the connection after a request. Or what can also happen here is some types of user input may cause this function to fail. And now we don't want this to fail because of user input, because that's just a simple DDoS of our service. So we need to handle the error. So for now, let's handle it the same way we would handle the failure on the respond function call. And instead of respond, we just say receive. Okay. Now, the problem here is if we break now, we'll jump out of the outer while loop. And we don't want to jump out of the loop. We just want to return back to the start of the loop and try again to accept another connection. So what we'll do is we'll just move this into the inner loop. So now if it breaks out of the inner loop, then the outer loop will just start over again, accepting new connections. Okay, so let's just give that a quick test run. Okay, so I'm going to call curl again. And what we see at this point is that we elegantly handle that connection closing on the receive call. Now, there's another big problem with our application, and that's that all the instructions in the start server function will be executed sequentially, and our application's running with a single thread. So what this means is the single thread would accept a connection from the socket it listens on, and then the execution will continue in this while loop indefinitely, or until that connection is closed by the client. Now, only once that connection is closed, or if we had a failure on the connection, the thread will return to the outer while loop where it will accept a new connection. So as a result, only one connection can be serviced by this server at any given moment in time. So let's quickly demonstrate that. So we've got our application running. Now what I've got in this desktop is I've got a terminal and a web browser. So in the terminal we can continue to run curl and show that we get the hello world response. And on the right hand side I've got the web browser, so we can open that port in the web browser. Now the problem with the web browser is that it will keep the connection open in case we want to have other requests for that server. I think this is probably just more efficient if you've got a thick JavaScript client inside the browser. Okay, now if we try to open curl, run curl again, now suddenly curl gets stuck because it's waiting for that connection to be released. Now killing the web browser may release the connection, so let's try that quickly. Okay, so once we killed the web browser, now suddenly curl can continue to function. Hey folks, Joe from the editing floor with a quick Wireshark demonstration of what we just saw. We're listening on the loopback device, filtering TCP traffic on port 8000. If we repeat the curl exercise, in the beginning we can see some fairly standard TCP handshakes for establishing a new connection. Once the connection is established, the curl client sends through the HTTP request and the application server responds with an HTTP response. Afterwards, the curl client initiates the close handshake, and we can see that this is acknowledged by the server and the TCP connection is closed. Okay, so in contrast, if we repeat the exercise with the web browser, again in the beginning we can see fairly standard handshake for establishing a new TCP connection. Then we can see that the web browser sent through the HTTP request, and the application server responded with an HTTP response. Now, what we can see here at the end is that there is no initiation of the close connection handshake like we had with the curl client. So at this point, the TCP connection is still open. So if we try to repeat the curl exercise, we can see that there's this handshake to establish a new TCP connection, which succeeds, and the curl client sends through the HTTP request. However, at this point, the application server is still busy processing the stream from the browser, so it cannot service the new requests from the curl client. And what we see here is some TCP keep alive messages, which I think originates from the web browser. Okay, so for the application to service multiple connections, this while loop needs to run asynchronously. So that way the application can continue to accept new connections while it's also servicing existing connections. Now, what we can't have is we cannot have shared buffers between different connections. So the buffers would also need to move into the same memory space as the asynchronous tasks. Now, to use the ZigIO interface for asynchronous calls, I will need to create a new function. So let's call that function service stream. So the first parameter will be our IO parameter. And then we need the stream parameter, which would be stdio, net stream, and it won't return anything. Now what we can do then is we'll need to move all of this into that new function, and we'll also have the stream close function called inside the new function, because we only want the stream to close once the new function is done with it. Cool. Okay, so that's basically just moving the code around. And now to have the exact same functionality that we previously had, we'll just pass through the stream and the IO parameters. Let's fix that typo. Cool. Okay, so it's never mutated, so let's change that to a const. Some finger trouble over there. Okay, so let's just compile the application to see that I didn't break anything. Okay, let's test that. Okay, cool. So it's still working the same way it did before. Okay, so the final thing we need to do to make this asynchronous is we need to call the async function on the IO interface. Now the first parameter will be the function pointer, and then our second parameter is the parameters for the function. Now the async function returns a future, which is a handle for this asynchronous task. Now I'm just going to ignore it because there's nothing for us to do with the service stream function. It doesn't return a result, and we want it to stay alive for as long as the server's running. Okay, so let's give that a quick test run. So we've got our server running in this terminal. Now I'll switch to a desktop with two clients. So on the left we can run curl, and we can see that curl's happy. Now if we go to our web browser and we open the socket, we can see that the web browser can get the hello world message. Now, as we already established, the web browser will keep this connection open. So we can go back to our terminal. Now, previously, curl would have not been able to get a connection serviced at this point. But as we can see, our server is now completely fine servicing multiple connections. Now there's one more thing that's bothering me, and that's this parse IP4 function call over here. Now first of all, we are passing it the address for the loopback device. Now there are utility functions for getting an address of a loopback device. Second of all, parsing can fail, so we're introducing yet another failure point in our server code. So what I'll do is I'm going to change this, that we just initialize the struct directly. So let's delete this, and we initialize that address. Now there's some utility functions on the IP4 address struct, and I'm just going to say that we want the loopback device with the listen port. Okay, now inside this IP4 address we also have an unspecified utility function. Now we'll use this if we want the application server to listen on all the IP addresses of a host. Okay, so let's save these changes, and we just build and run to see that I didn't break anything. Okay, so that looks good. Now there are situations where a host may have multiple IP addresses, and we want the application server to listen only on one of those IP addresses. So in that case, we would definitely need to parse the IP address string. However, a typical deployment situation is that we've got a reverse proxy that is exposed to the outside world, and our application server is running in a protected area of the network that only the reverse proxy can reach. So in that case, our application server would either just need to listen on the loopback device, or it would need to listen on an unspecified address, so it would accept connections from all IP addresses of the host. Anyway, so now the interwebs have yet another example of an HTTP server implemented with ZIG 0.16. So hopefully this video is helping some people. Anyway, if you enjoyed this video, click on the like button. If you want to see more, click subscribe, and I will see you in one of my next videos. See ya.